In this video, we'll explore how to create a Minecraft-like game. Minecraft's success lies in its simple yet engaging mechanics, where players can explore and interact with a voxel-based world. Our goal today is to provide an overview of the essential steps involved in building such a game. Minecraft-like games are known for their open-world exploration, player-driven mechanics, and the ability to manipulate the environment. At the core of these games is the voxel system, which is a method of representing the world as a grid of cubic units. The game world is built from blocks, with each block representing a small chunk of the terrain. The design of these games encourages creative freedom, with players able to mine resources, craft tools, and build structures within the game world. The procedural generation of terrain allows for an almost infinite variety of environments, keeping the game fresh and ensuring that no two playthroughs are alike. Understanding these systems is essential if you want to build your own Minecraft-like game. In this presentation, we will cover the core technical components that make up the game, such as chunk management, procedural generation, voxel rendering, and multiplayer mechanics. By the end, you will have a clear roadmap for how to approach the development of your own game. Choosing the right game engine is crucial as it serves as the foundation for your development efforts. Unity is a popular choice for Minecraft-like games due to its versatility, extensive community, and asset store. It's especially useful for small to medium-scale projects. Unity's C# scripting and built-in physics engine make it easy to develop complex interactions without needing to write everything from scratch. Unreal Engine, on the other hand, is suited for high-end graphics and large-scale worlds. Its C++ framework provides fine-grained control over performance, but comes with a steeper learning curve. Godot is an open-source engine that is lightweight and ideal for simpler games, or if you have fewer resources. The open-source nature allows you to customize the engine as needed, making it a good option for small indie teams. The key factor in selecting the right engine is considering the scope of your project, your team's expertise, and the performance needs of your game. It's essential to pick an engine that aligns with your technical skills and the requirements of your game. In a voxel-based game, the world is represented by 3D pixels called voxels, which are cubic elements that make up the environment. Each voxel can store various types of data, such as terrain type, block state, or properties, like durability. The flexibility of voxels allows players to interact with the world by mining, placing, and destroying blocks, creating a dynamic and editable environment. In contrast to polygon-based graphics, which use triangles and vertices to represent surfaces, voxels are simpler to manipulate but can be more expensive to render, especially in large quantities. Efficient data management becomes a challenge when the world is composed of millions of individual voxels. Each voxel needs to be processed and rendered in real time, which can put significant strain on system resources. Techniques like chunking, where the world is divided into smaller sections, and level of detail, LOD, for distant chunks, can help alleviate performance issues. Understanding voxel systems is crucial as they serve as the backbone of the environment, and optimizing them will be one of your key tasks in building the game. The chunking system is designed to make the world manageable by breaking it into smaller, more digestible pieces. Each chunk is typically made up of 16 by 16 by 16 or 32 by 32 by 32 blocks, though this can vary depending on the desired performance. The idea behind chunking is that instead of loading the entire world at once, which would be computationally expensive, you only load and render the chunks that are near the player's viewing frustum, the area the player can see at any given time. Dynamic chunk loading ensures that as the player moves, new chunks are loaded into memory, and chunks that are no longer visible are unloaded, keeping the system's memory usage low. Efficient chunk management is crucial, especially when generating large, procedurally generated worlds, as it ensures that the game runs smoothly even with vast environments. The performance of the game depends largely on how well you manage these chunks, especially in terms of memory usage and rendering performance. In multiplayer, you'll also need to account for synchronizing chunks across different players. Procedural generation is a key technique used in Minecraft-like games to create infinite, dynamic worlds. It allows you to generate a vast world on the fly, meaning you don't need to store large amounts of pre-built data. The terrain, such as mountains, valleys, and oceans, is often created using Perlin noise or simplex noise, which generates smooth, natural-looking patterns for elevation, allowing for more realistic landscapes. These algorithms create continuous gradients, so there are no sharp, unnatural transitions. Additionally, you can layer different biomes over the terrain, such as forests, deserts, and mountains, each with unique characteristics. Caves, rivers, and even oceans can be procedurally generated to add variety. This method allows the world to be generated on the fly, based on seed values, meaning that the same world can be generated consistently using the same seed. Procedural generation can create an infinite number of unique worlds, making the game feel expansive and providing nearly endless exploration opportunities. However, it's important to balance complexity and performance. Highly detailed worlds can be computationally expensive. Block interaction is one of the defining features of Minecraft-like games. The core mechanic is the ability to mine and place blocks in the game world, which is done through raycasting. Raycasting is a technique where a ray is cast from the player's viewpoint or mouse pointer to determine which block the player is interacting with. This allows for actions like mining or placing a block. Different tools can affect the speed and efficiency of mining. For example, a pickaxe will break stone blocks faster than bare hands. Blocks also have specific properties like durability, how long it takes to break a block, and resource types, which determine what item is dropped when mined. For example, mining a tree might yield wood, while mining a stone block might yield cobblestone. Ensuring smooth, responsive interactions and considering the underlying physics of block destruction, e.g., blocks breaking into smaller pieces, is essential for immersion. Player movement is another key technical challenge in Minecraft-like games. The player needs to be able to walk, jump, and even fly through the world. Implementing gravity ensures the player stays grounded and follows realistic physics. The character controller component in Unity is often used to handle player movement, as it provides built-in collision detection with the world's terrain. Alternatively, the rigid body component can be used for more complex physics interactions, especially when dealing with forces like gravity or player velocity. It's important to handle collision detection properly, ensuring the player cannot pass through solid objects or terrain. For larger worlds, it's essential that player movement is smooth and responsive, even as the game world grows. To achieve this, the physics system needs to be optimized, ensuring the game can handle the player's movement in real time without performance issues. Rendering is a complex and resource-intensive process in a Minecraft-like game, especially with a large number of voxels. To optimize rendering, the first step is to implement frustum culling, which ensures that only the chunks within the player's field of view are rendered. This prevents the game from rendering blocks that are far away and not visible. For distant chunks, you can implement level of detail, LOD, where chunks that are far from the player are rendered with lower detail to save resources. For example, instead of rendering each voxel individually, you can combine distant voxels into larger blocks. Another important consideration is multi-threading, where the chunk loading and rendering processes are split across multiple threads. This prevents the game from freezing while loading new chunks or updating the terrain. Properly implementing rendering optimizations is critical to maintaining high performance in a voxel-based world, particularly in large, procedurally generated environments. In a Minecraft-like game, chunk streaming allows chunks to be loaded and unloaded dynamically as the player moves through the world. This process ensures that only the relevant chunks are loaded, preventing the game from bogging down the system. To achieve smooth gameplay, background threads are often used to handle the processing and loading of chunks. These threads run asynchronously, meaning they do not block the main game loop. However, managing multiple threads requires careful synchronization to avoid issues like data conflicts or deadlocks, where threads attempt to access the same resources simultaneously. By carefully managing background loading, you can prevent stuttering during gameplay, ensuring that new chunks load seamlessly as the player moves through the world. For a multiplayer game, you will need a client-server architecture, where one server manages the world state, while multiple clients, the players, interact with the server. The server is responsible for maintaining the authoritative world state, ensuring that all players are seeing the same environment and making actions that are synchronized across all clients. Player actions like placing blocks, crafting, and moving need to be synchronized between clients to ensure consistency. Additionally, network latency can affect the game experience, so you need to account for lag compensation and ensure smooth gameplay despite network delays. Techniques like prediction, where the client estimates the player's next actions, and server reconciliation, where the server corrects the client's actions when necessary, are critical for making sure that multiplayer gameplay is smooth and enjoyable for all players. In Minecraft-like games, one of the most important features is the ability for players to edit the terrain by placing or breaking blocks. This interaction requires frequent block state updates in the world. When a player breaks a block, it must be removed from the game world, and new data must be generated for any surrounding blocks that may have changed state, e.g., a newly exposed block might need to be recalculated for light levels. Similarly, when a player places a block, the surrounding blocks must be updated to reflect the new placement. However, frequent block updates can cause performance issues, especially in areas where players are making large modifications to the world. One way to manage this efficiently is to implement a local update system where only the blocks around the player's immediate area are updated in real time, while larger chunks or distant areas are updated in the background. You can also implement chunk recalculation techniques that only update affected chunks, rather than recalculating the entire world after each player action. The lighting system in a Minecraft-like game is crucial for making the world feel immersive and alive. A basic lighting system includes ambient lighting that provides a soft, diffuse light throughout the world, and dynamic lighting that changes based on the time of day or light sources within the game. Lighting systems should simulate realistic effects such as shadows, light propagation, and how light levels change when a block is destroyed or placed. The day-night cycle is a key aspect of many Minecraft-like games, and this can be achieved by transitioning between light levels over time. To optimize performance, a technique called light maps is often used, which pre-calculates lighting information for static objects. For dynamic objects or areas with changing lighting, like a torch placed by the player, you would use real-time lighting calculations. Balancing real-time lighting with light maps allows you to create a visually rich environment while minimizing the computational load during gameplay. In Minecraft-like games, the inventory system allows players to collect resources, store items, and craft new objects from the materials they gather. Managing this system involves several key components, including inventory management and a crafting system. The inventory system must handle items of different types, tools, resources, etc., and track quantities, allowing players to interact with these items through a simple user interface, UI. Crafting often involves recipes, where certain combinations of resources result in the creation of new items or tools. The UI should allow players to see their inventory and interact with items easily. For multiplayer games, synchronization is important. The player's inventory state must be consistent across all clients, and any changes, such as adding or removing items, should be reflected in real time. Server authority is also important, as the server manages the world state and player actions to prevent cheating or discrepancies between clients. Audio plays a significant role in making Minecraft-like games immersive and engaging. To create a more realistic world, ambient sounds like birds chirping, water flowing, and wind rustling can add depth to the environment. These sounds should change based on the player's location or the environment's conditions, e.g., moving through a forest should trigger different sounds than walking through a desert. Additionally, sound effects are crucial for actions like breaking blocks, placing items, and jumping. These sounds help provide feedback to the player and reinforce the feeling of interacting with the world. To further enhance the experience, dynamic background music can be used, adjusting its intensity based on the game's environment, e.g., calm music in a village, tense music in a cave. Finally, spatial audio is essential for immersion. Sounds should change in volume and direction based on the player's position relative to the sound source. This creates a more believable and interactive world. Proper implementation of these audio features can significantly improve the player's experience. For a Minecraft-like game to work well in multiplayer, the networking system must be efficient and reliable. A client-server architecture is often used, where the server is the authoritative source of information about the world, while the clients are responsible for displaying this information to the players. UDP is typically used for faster, more efficient communication, as it reduces the overhead compared to TCP and is well-suited for real-time multiplayer games. However, UDP does not guarantee message delivery, so you may need to implement reliability and error correction protocols. Lag compensation is essential for ensuring smooth gameplay, especially when players are far apart on the server. Techniques like client prediction, where the client anticipates player actions, and server reconciliation, where the server corrects the client's actions, help mitigate the effects of latency. In addition to lag compensation, network optimization is critical. Minimizing the amount of data sent over the network by compressing data or only sending updates when necessary ensures that the game runs smoothly even with multiple players. Allowing players to create mods or custom content can greatly enhance the longevity and replayability of a Minecraft-like game. By providing a robust modding API, you expose certain game mechanics and systems to players, allowing them to create new items, biomes, or even game modes. This extensibility can help build a thriving community of modders and players. It's important to offer documentation and tools that guide modders on how to create content compatible with your game. These tools might include an asset importer for custom models or textures, a scripting language for creating new mechanics, or a world editor for designing new maps. However, care must be taken to ensure that mods don't destabilize the game. One way to handle this is to provide a mod validation system that ensures mods are properly tested and don't interfere with core game functions. Regular updates and mod compatibility checks are also essential for keeping the game stable while introducing new user-generated content. Minecraft-like games often feature massive worlds, sometimes procedurally generated and practically infinite in size. Managing such large worlds requires efficient handling of world streaming, where parts of the world are loaded or unloaded as needed based on the player's location. To prevent excessive memory usage, chunk storage is often handled dynamically, and unused chunks are removed from memory. Compressing chunk data and using seed-based world generation ensures that worlds are reproducible. The same seed will generate the same world, but still feel vast and procedurally unique. Level of detail, LOD, can also be applied to reduce the load on the system by simplifying distant chunks. Additionally, the world data must be optimized so that it doesn't become too heavy on memory or disk I/O. Chunk compression algorithms like run length encoding, RLE, or delta compression can help reduce memory consumption. Balancing the size of the world with performance is essential to maintaining a seamless gaming experience. In Minecraft-like games, NPCs, non-player characters, add life to the world, whether it's friendly villagers, passive animals, or hostile monsters. To make NPCs behave naturally, you can use techniques like finite state machines, FSMs. An FSM is a model where NPCs are in different states, such as walking, sleeping, or attacking, and transition between these states based on certain conditions, e.g., the NPC becomes aggressive when the player is nearby. For movement, NPCs need to be able to navigate the terrain, which is where pathfinding algorithms like A** asterisk come into play. Asterisk is used to find the shortest path from one point to another on a grid-based map. NPCs also need to interact with the environment. For example, villagers should be able to work, sleep, and trade, while monsters might hunt the player or hide during the day. Adding depth to NPC interactions can significantly enhance the gameplay experience. In Minecraft-like games, progression and gameplay goals help keep players engaged. One way to implement progression is through quests and challenges, where players are given specific objectives to achieve, such as finding a rare resource or defeating a boss. These quests can be simple or complex and can provide rewards in the form of items, experience, or in-game currency. Adding an achievement system gives players additional long-term goals and rewards, motivating them to explore the world, build, or survive. The system can track a variety of actions like crafting, combat, exploration, and more. This creates a sense of accomplishment, particularly for players who enjoy completionism. By providing players with clear goals, whether short-term or long-term, you can enhance the gameplay experience and add replay value to your game. In conclusion, building a Minecraft-like game involves understanding and integrating a wide variety of systems: voxel rendering, procedural generation, chunk management, multiplayer architecture, physics, AI, and much more. Each of these systems needs to work together to create an immersive and fun gameplay experience. However, it's important to keep performance in mind throughout development, especially when dealing with large, procedurally generated worlds. Focus on optimization techniques like chunk streaming, LOD, and multithreading to ensure the game runs smoothly. Building a Minecraft-like game is a challenging but rewarding process, and it's important to remain flexible and willing to iterate on your systems. With careful attention to the technical aspects and an understanding of the systems at play, you can build a game that captures the essence of Minecraft while adding your own unique touch. Thanks for watching! For more AI materials and games, please go to bowsy8.com.